now. Just let me double check. No dobrze, moi drodzy, prawdopodobnie mnie słychać, więc witam bardzo serdecznie dzisiaj na naszej kolejnej prezentacji z cyklu Nurkowie Pomagajmy Sobie. Dzisiaj naprawdę wspaniała prezentacja, sam nie mogę się doczekać, aż się usłyszę. Przede wszystkim po raz kolejny chciałbym wszystkich Was serdecznie powitać i przypomnieć, że nasze prezentacje w ramach akcji Nurkowie Pomagajmy Sobie organizowane są po to, żeby zwrócić uwagę świata, Polski, wszystkich nas dookoła na trudną sytuację związaną z koronawirusem dla centrów i baz nurkowych. Tradycyjnie bardzo Was mocno prosimy o wsparcie dla centrów baz nurkowych. Na dole zawsze znajdziecie link do strony nurkowiepomagajmysobie.pl. Tam losowo wyświetlane są w losowej kolejności centra i bazy, które do naszej akcji się zapisały. Jeżeli uważacie, że nasza akcja jest słuszna i podobały Wam się prezentacje, możecie wspomóc naszą akcję wpłacając dowolną kwotę na dowolne centrum nurkowe i pomóc naszej akcji. No więc dzisiaj naprawdę wspaniały dzień. W kwestii informacyjnej w tym samym czasie na naszym kanale YouTube odbywa się transmisja tej samej prezentacji w oryginale, ponieważ ta tutaj na Facebooku będzie tłumaczona. Tutaj chciałbym bardzo, bardzo podziękować Michałowi Skoczyńskiemu, firmie Redu za pomoc w organizowaniu tego całego przedsięwzięcia. Michał, naprawdę nie wiem, nie potrafię znaleźć słów, żeby wyrazić naszą wdzięczność dzięki temu, że tak naprawdę ta prezentacja będzie tłumaczona na język polski tylko i wyłącznie dzięki Twojej pomocy, więc jeszcze raz bardzo duże podziękowania. Dla tych, którzy chcieliby jednak usłyszeć ją w oryginale, w opisie do tego streamu na Facebooku znajdziecie link do naszego kanału YouTube. Tam ta sama prezentacja będzie miała miejsce bez tłumaczenia, czyli w oryginale, więc możecie sobie wybrać, czy chcecie słuchać z tłumaczeniem, czy chcecie słuchać bez tłumaczenia. Jeszcze raz, na Facebooku będzie z tłumaczeniem symultanicznym, na YouTubie będzie w oryginale. Moi drodzy, to tyle gwoli wstępu, więc czas na naszego pierwszego gościa. Oddaję mikrofon Michałowi. Michał, kto będzie naszym gościem? Kto to będzie? Kto to będzie?
Prezentacja, którą zaraz usłyszycie, będzie prowadzona przez Simona Mitchella. Simon Mitchell jest profesorem anestezjologii na Uniwersytecie Auckland w Nowej Zelandii, czyli ta prezentacja, którą będzie robił, u niego już jest niedziela rano, tym bardziej to doceńmy. W przeszłości Simon był oficerem medycznym w marynarce wojennej. Sam jest zapalonym nurkiem wrakowym i rybreaderowym. Wykonał ponad 6000 nurkowań, w tym nurkowania rekreacyjne, techniczne, naukowe, zawodowe i wojskowe. Jest autorem ponad 150 publikacji, w tym współautorem takiej Biblii medycyny nurkowej Diving and Subaquatic Medicine 5. edycji. Jest też lekarzem dyżurnym dla wypadków nurkowych w szpitalu w Auckland i jego ostatnie ekspedycje rybreaderowe to wrakowisko w Lagunie Truk w listopadzie 2019 roku, a w lutym załapał się jeszcze na jaskinię Pierce Resurgence w Nowej Zelandii. Więc powitajmy wspólnie Simona. Simon, the floor is yours.
Thanks, Michal. Look, I'll just try and share my screen with you guys, make sure that that's all working before we do anything else. So you see my screen now, Michal? Or the team? I'm assuming you are. Someone will tell me if you're not. Well, look, good morning, everybody. From New Zealand, early in the morning. You'll be able to see the sun coming up behind me here. It's just after 7 in the morning. This is a new experience for me. Some of you know that I do a lot of speaking at conferences, but doing these sorts of things online is different. You don't have the immediacy or contact with an audience. And so I'll probably just stick to the facts today, not try and tell other stories or crack jokes or anything, but hopefully you'll still find it a valuable experience. As I talk about this most controversial of technical diving subjects, what is optimal decompression? Many of you will be aware that this is a subject that has been debated extensively on the internet. I've been involved in a lot of those discussions, and I'll return to this theme later, but one of the things I want to point out to you is that I'm a scientist, and as such, it is very important for me and my professional reputation that I stick to the facts that are provable from evidence. And so I'm going to be presenting you with the facts as they exist as of today in May 2020, and try and keep the speculation to a minimum. You'll probably note that my cadence today is slightly slower than I would normally speak. That's because this is being simultaneously translated into Polish by Michael, who is going to be working very hard over the next hour, and I'd like to thank him personally for what he's doing. I'm going to approach this from what I would consider a very simple to more complicated pathway. I'm going to talk about quite a lot of basic stuff first. The idea is that we carry everyone along with us. I should apologize to those of you who already know a lot about this subject, because much of it will be very basic for you, and I'm not trying to insult your intelligence. And finally, before I start, I want to thank Professor David Dulett, a colleague of mine from the Naval Experimental Diving Unit in Florida, from whom I've learned much of what I know about decompression, and also Kevin Wats, who I've never actually met, but Kevin is an American who is very clever with his maths and has pioneered some very illustrative means of showing the sorts of principles that I'm going to be talking about today, and I'll be using some of his diagrams as we go through this presentation. So that's actually David Dulett and I, slightly younger photo. It's about 16 years ago at a seminar we ran in Australia. David on his way to the United States about that time to work for NEDU. This is one of Pete Mesley's photographs of me underneath the Nagato, a Japanese battleship at Bikini Atoll. Those are the stern guns. And Pete is another person who I've learned a lot from in the photography world over the years. So the question we're aiming to answer today is, what is the optimal approach to decompression planning in technical diving? And what in starting to answer that question, I'd like to take you just very briefly through the process that we all go through when we're planning a technical dive. So the first thing we do is we decide on a depth and a bottom time and the gases that we're going to breathe. And once we have that information, we then consult a decompression planner. And there's a number of those. It could be Bullman gradient factors, it could be VPM, it could be RGBM, whatever decompression planner you choose. And that will give us a decompression plan for our dive. of X minutes duration. So we might be going to 100 meters for 25 minutes, and our decompression planner tells us we've got to do 2 hours of decompression, 120 minutes of decompression. The question that should be occupying our minds in contemplating this decompression is this: does the decompression plan, so by that I mean the depths and times of the decompression stops, does it produce the least risk for the amount of time that we're going to be decompressing? So in my example, I said 120 minutes. Is our stops and depths, so stop times and depths, giving us the least risk for that duration of decompression? So let's put that another way. For a given duration of decompression, what distribution of stops at different depths and times will give the least risk? Now, these are words, right? I'm actually a visual person. So let's try and illustrate this principle using a diagram rather than words. So here is a decompression plan. Don't worry about the depths and times. That doesn't matter. It's just to illustrate a principle. So this plan says we are going to spend the amount of time decompressing indicated by this red arrow. The question is this distribution of stops and times going to give us the least risk for that duration of decompression? Or could it be that we could do it this way and have least risk? Or so less emphasis on deep stops, more emphasis on shallow stops. Or could it be that doing it this way would produce least risk? So more emphasis on deeper stops and less emphasis on shallow stops. So one of the things you'll notice about this illustration is that all of these profiles are the same length. And it's important to understand that if we want to study the effects of distributing our decompression stops in different ways, as shown here, you have to have the profiles the same length. Otherwise, you can't comment on the effects of the different stop distributions. Now, some people say to me, well, why are you so obsessed with having the profiles the same length? So for example, someone might say, I have a profile, I have a planner that gives me a profile that looks more like this. And they say, why can't I just compare one of these profiles with this one, this longer one? And of course, you could do that. You could compare this profile here, which has more emphasis on deep stops, but a longer period of shallow stopping, with this one, with less emphasis on deep stops, but a shorter overall profile. You could compare those and you could figure out which one's best. It would probably be this longer one, because the longer the decompression, the safer the decompression should be. The problem with this approach is you can't make any comment about the different distributions of these stops because you can't separate that from the length of the decompression. If you want to do that, you have to have the profiles the same length. Now, the other thing to remember too is that if you have this longer decompression, you're still going to be asking yourself the same question. Is this distribution of decompression stops the safest or giving me the least risk? Or could it be that if I do these shallower stops and just make the shallowest stop in this decompression the same length as this deeper stop approach, could that be even safer? So even though you're making this profile, the deeper stop profile, longer, you still have to ask yourself the same question about the distribution of decompression stops. So the point I'm trying to get to here is that if you want to comment about how you distribute your decompression stops in a study, you have to have the profiles the same length. Otherwise, you can't answer that question. Okay, so with that background in mind, let's now move on to a little bit of decompression physiology 101. So this is where I expect that there'll be quite a few of you who know this material very well, and I apologize to you if I'm insulting your intelligence, but there'll probably be others who find this useful. This is a very simple model of the way that gas is distributed through the body. And of course, the system is designed to supply our tissues with oxygen and remove carbon dioxide from those tissues as oxygen is metabolized. So here is the lung, the arterial blood, carrying oxygen from the lung off to the tissues, and then the veins carry carbon dioxide away from the tissues and back to the lung where it's eliminated. Now, of course, what we're interested in is the transport of inert gases around this system. So the inert gas that we're most commonly interested in is nitrogen. And let's just say that we're all sitting here now, air breathing, and we probably have been for some time because it's COVID-19 and nobody's diving. And so we are what you might call saturated with nitrogen at the pressure that we're currently breathing it. So nitrogen is evenly distributed throughout our bodies, the same pressure of nitrogen in the lungs, in the arterial blood, in the tissues, and in the veins. Okay, so what happens when we dive? We're going to descend breathing air down to depth. So the pressure that we're surrounded by, the ambient pressure or the depth pressure, increases. And that means that the pressure of nitrogen that we're breathing increases. That is virtually instantly transmitted into the lungs. And similarly, it is transferred, that same pressure of nitrogen, almost instantly into the arterial blood. And the arterial blood carries it off to the tissues. Now, what doesn't happen instantly is the equilibration of the nitrogen pressure in the tissue and the arterial blood. That takes time. So that happens more slowly, and the rate at which it happens is dependent primarily on the amount of blood flow to the tissues. So the more blood flow the tissue receives, the faster this process of nitrogen moving into the tissue will occur. Now, what I want to do is illustrate this process that I've just described on a graph. So we're going to take the three parameters or the three things of interest here, put them on a graph. So those things are the depth pressure, the pressure of nitrogen in the arterial blood, and the pressure of nitrogen in the tissues. So let's take those three things and put them on a graph. So here's our graph. We have pressure on the y-axis and time on the x-axis. Of course, we start at 1 atmosphere pressure, and our depth pressure increases quickly, and we've gone to 4 atmospheres, which I'm sure you all know is 30 meters. And as I said before, the pressure of nitrogen in our lungs and in our arterial blood increases almost straight away. But the increase of the pressure of nitrogen in the tissues takes time. And that, as I said before, depends on the amount of blood flow that the tissue gets and a few other factors. Now, of course, different tissues have different amounts of blood flow, and so they will behave differently than this one single tissue that I've illustrated here. So here's a tissue that is got lots of blood flow and equilibrates with nitrogen very quickly. And here is a tissue that has got poor blood flow and equilibrates much slower. It would take, days for that to equilibrate with the arterial pressure of nitrogen. But let's just stick with our one tissue for the moment. So now we're going to turn around and come back up. And let's track what happens when we do that. So now the depth pressure is decreasing, and whoops, I didn't mean to do that, but we'll get to that in a minute. So the pressure of nitrogen in the lungs is less, and the pressure of nitrogen in the arterial blood is therefore less. And now nitrogen from the tissue, where the pressure is higher than in the arterial blood, will start to move into the blood to be carried back to the lungs, where it is eliminated by breathing. And if we take those things back to our graph again, we can see that the pressure surrounding us, the depth pressure decreases. We go back to 1 atmosphere. Pressure of nitrogen in the arterial blood decreases very quickly. And so pressure of nitrogen in the tissues will fall as nitrogen leaves the tissues and is carried away to the lungs to be breathed out. But just like it took time for this to happen when we were taking nitrogen up, it takes time for this to happen when we're eliminating the nitrogen. And this is probably the first place we get to a critical concept in this presentation. And that is that for a period of time, the pressure of nitrogen in the tissue is higher than the ambient pressure or the surrounding pressure. You can see that that is the case in this zone here. And we refer to that as tissue supersaturation. That is, the pressure of nitrogen in the tissue is higher than the surrounding pressure. Now, this is a slight simplification of the real situation, because when you're calculating supersaturation, you take into account dissolved oxygen and carbon dioxide and water vapor, but we'll just keep it simple and deal only with the nitrogen. So we have this period of supersaturation. So what? Well, this is critically important because it's supersaturation of dissolved gas that is the fundamental condition required for bubbles to form. It is supersaturation that drives bubble formation, and as you know, bubble formation is what ultimately produces the symptoms of decompression sickness. Now, another concept that is good to introduce at this time is so-called integral supersaturation. And what this is just an integral of supersaturation and time. So the degree of supersaturation and the length of time over which it persists. And it's simply the area under that curve there So inside that shaded area that you see on this graph is the integral of supersaturation amount and time. And why is that important? Well, the higher the supersaturation, the more likely bubbles are to form. And the longer the period of supersaturation, the more time they have to grow. And this integral of supersaturation and time is a good overall measure of the supersaturation stress that's driving bubble formation. So the higher the integral supersaturation, the more likely it is that bubbles will form and grow over time. All right, so I just wanted to return to this idea that we've only been illustrating one tissue. And obviously, if you're calculating the integral supersaturation, you need to do it for all the different tissues that are involved in taking up and losing nitrogen in the body. And this ends up being quite a complicated process. So you end up with diagrams that look a bit like this. This is just the same as the one I showed you before, but with 16 different tissues, the 16 tissues that Bullman modeled when he designed his decompression algorithm. And the black line represents the decompression and the decompression stops. And you can see all these highly colored lines, each one representing a different Bullman tissue. And if we were calculating the integral supersaturation for this dive, we would be looking at the area under the curve for each one of these 16 tissues where it is above this black line. So all of this area in here for the 16 tissues combined over here as well, and then added together to get a single number for the total integral supersaturation for that dive. And this concept is one that I will return to later in the presentation. Okay, so we change direction here a little bit. And what I want to do now is show you another way of depicting decompression. And this one is designed to help us understand how the different decompression models work. So far we've talked about tissues taking up nitrogen, losing nitrogen, how tissues become supersaturated, and a concept for quantifying supersaturation, this integral supersaturation. Now we're going to look at decompression illustrated in a slightly different way. This is actually one of my pictures of David Dulett at a place called Northern Arch at the Poor Knights Islands, just a 2.5 hour drive north of where I am now. Beautiful dive. New Zealand has great diving, a bit of gratuitous advertising for the New Zealand diving industry and tourism here, because we need your money after COVID-19. But no, beautiful diving, world-class temperate water diving. Okay, so I've put two axes on this slide. This is ambient pressure or depth, and this is the tissue gas pressure. Now, look, if you're going to sleep at this point, it's a good time to wake up, because the next part of this presentation depends a lot on you following this paradigm, this way of illustrating decompression that I'm showing you here. Let's work through what happens to these two things, ambient pressure, depth, and tissue gas pressure during a typical dive. So at the start of the dive, the ambient pressure or depth is going to increase quickly because we're descending, right? So we can illustrate that with this line. As we're descending, the ambient pressure is increasing quickly. The tissue gas pressure, well, will start to take on gas, but it takes time. And let's just say we stop at this depth here. This is our bottom depth. We're swimming around a wreck now. So we're not changing our depth. But what will happen over time is that the tissue gas pressure will increase. We'll start to take on inert gas. So tissue gas pressure starts to rise. The depth isn't changing. Now, time is not illustrated on these graphs, so you just kind of have to imagine time. You might say, okay, how high can this go? Well, think about that. What is driving the inert gas into the tissue? It's the pressure that we're breathing it at, or the ambient pressure, the depth. So if we draw a line where tissue gas pressure equals ambient pressure or depth, then you think about it, the tissue gas pressure can't go any higher than that line unless you go deeper, because it's the depth pressure or the ambient pressure that is driving the gas into the tissues. So if we stay at depth long enough, then eventually, if let's just say we're following one tissue here, its gas pressure will eventually equal the ambient pressure, approximately. Again, these diagrams are a simplification of a moderately complicated picture, but for our purposes, they work fine. And at that point, we would say that this tissue is now saturated with inert gas at this depth. You can't get any more gas into the tissue unless you go deeper and provide more gas pressure, more pressure to push the gas into the tissue. So this tissue is now saturated. Now, of course, there will be tissues that are slower to take up inert gas. So at the same point in time, there'll be some other tissues that have not taken on the same amount of gas. Their tissue gas pressures after the same amount of time will be lower. They're those slower tissues that you saw on that diagram earlier. But let's just focus for the moment on this one tissue that we'll assume has become saturated, just because it makes the diagram easy to follow. So now what happens when the diver begins to ascend? Well, obviously the ambient pressure or depth is going to decrease. And as we ascend and breathe a lower pressure of nitrogen, we'll start to eliminate it. So the tissue gas pressure will fall, but probably not as quickly as the depth pressure or the ambient pressure. So it'll look a bit like this. Now, you can see what's happening here. As we ascend and the depth pressure or ambient pressure falls quickly, we fairly quickly get to a point where the tissue gas pressure is now higher than the ambient pressure. And you'll recall what I said before, that is essentially the definition of supersaturation. We have a higher pressure of gas dissolved in the tissue than the pressure surrounding us. And you'll recall that supersaturation is the fundamental requirement for bubble formation from dissolved inert gas. So this is very important. And at some point, we're going to have to stop so that this doesn't become too great, because it will drive bubble formation. And the whole idea of decompression strategies is that they limit supersaturation using decompression stops. So let's just say that we stop at this depth here. So we don't decrease the ambient pressure anymore. We stop right here and wait. What will happen? Well, the tissue gas pressure will have time to fall because we'll eliminate it. And that's the whole principle of decompression stops. They give time for the tissue gas pressure to fall before we keep decreasing the ambient pressure. So it should be fairly obvious to you that the critical question here is, how do we decide on the allowable supersaturation and therefore how far we can ascend before we have to stop? Well, there are different approaches to that. And those approaches fall broadly into two categories. The first is what we call gas content models. Now, this is the category into which Bullman decompressions and gradient factors fall. I'll talk about gradient factors a little bit later. But the principle upon which these models work is that they maximize tissue supersaturation. They allow you to develop supersaturation up to limits that were originally derived from theory and then refined by experiments and adjusted based on the outcomes of those experiments and to some degree real world use. But again, I'm a diagram man, so let's illustrate this with a diagram. The most famous of those gas content models is the Bullman ZHL 16 ascent rules. So ZHL stands for Zurich limits, and because Bullman was Swiss, and the 16 refers to the fact that he used or modeled 16 theoretical tissues in the body. So he would have had 16 diagrams like this one, because we're just looking at one tissue here. And so for every tissue, there's a supersaturation limit that you should not exceed. So the way that a Bullman decompression works is that you ascend until the tissue hits its supersaturation limit. You shouldn't go any further because the tissue will become more supersaturated than Bullman thinks you should allow. And so you stop at that depth. This will be your first decompression stop here at this depth. And you wait. And obviously when you wait, the tissue gas pressure will fall. And then you can continue ascending and you hit the limit again and stop and wait and then ascend again and stop and wait and so on until you can surface underneath the limit. That's how Bullman decompressions work. And as I say, there's 16 of these tissues, and whichever one is getting closest to its supersaturation limit at any stage of the decompression, it is the controlling tissue, and it will dictate when you stop. Okay, so that's the gas content model approach to decompression. Now, many of you probably who are listening to this would have been around at this time, but in the mid to late 1990s, we had a collection of circumstances that raised concerns about whether these gas content model decompressions were the best way of doing it. And those circumstances included the fact that we were seeing decompression sickness cases that occurred despite people sticking to the limits. Okay. Of course, now we know that that happens pretty much no matter what decompression algorithm you use. And the other thing that happened around that time was that the use of Doppler technology to monitor bubbles was occurring more frequently. And this showed that bubbles were being detected in our bodies after surfacing from these dives, despite using these gas content decompressions perfectly. And that raised concerns that we were letting too many bubbles form. And maybe we should be thinking about decompressing a different way. And so getting back to this diagram, the question was, is this, we've ascended here to our first stop. Is this amount of supersaturation too much? Are we allowing too much supersaturation early in the decompression, and should we change the way we do it? And that's when the bubble models emerged. So the idea of bubble models was that they limited tissue supersaturation to smaller values early in the ascent in order to reduce bubble. The idea was that they would reduce bubble formation according to models, complicated mathematical models of bubble behavior, initiation and growth. Quite complex stuff. But let's not use words, and let's use a diagram to try and illustrate this. So on this diagram, I've got the same gas content model decompression that I showed you before. And now I'm going to show you how a bubble model looked different to that. So these models predicted that smaller initial supersaturations would help prevent bubble formation. And so instead of this being our first decompression stop, the bubble models looked like this. So they would allow you to ascend a shorter amount of depth before you had to make your first decompression stop. So your first stop would be here instead of here. And what this means is that at your first stop, you've got far less supersaturation than you do with a gas content model decompression. And then the decompression would continue like this. So smaller ascents with much less supersaturation at each stop, until finally you would ascend to the surface. In fact, this is shown intentionally with higher levels of tissue supersaturation than in a Bullman model. And this was based on the assumption that by reducing the supersaturations early in the ascent, you would prevent or reduce bubble formation, and that would mean that you could actually ascend with higher degrees of supersaturation later in the ascent because you've controlled bubble formation early. That actually meant that the early bubble models predicted shorter decompressions and quicker ascents overall than the gas content models that they replaced. So that's just a quick summary of how gas content models and bubble models differ in their fundamental approach to decompression. And you can see why the use of bubble models has become synonymous with the concept of deep stops, because they basically force you to do stops that are earlier and deeper, than a gas content model. Okay, so very early on, in the use of bubble models, it became essentially a belief, a strongly held belief amongst technical divers that bubble model or deep stop decompressions were a superior approach. And it is fascinating to reflect on that, because this belief was entirely based on what I will call theoretical attraction. Just the idea that these smaller supersaturations early in the ascent would prevent bubble formation and therefore be protective from decompression sickness. It is an attractive theory. And in fact, as you were listening to me, you're probably thinking, wow, what a great idea, you know, that would obviously work. And that's what we all thought, of course. But as time has passed, and this is where I'm headed now, we have started to see evidence that that theory may not be correct, but we're going to come to that. This is actually a photograph of Richard Harris. It's one of my photos from the Pierce Resurgence this year, just a couple of months ago. Richard is an anaesthetist colleague of mine from Adelaide in Australia. Richard and Craig Challen, who was also at the Pierce, were in the cave with the kids in Thailand. In fact, Richard was the anaesthetist who anesthetized them to be brought out. Richard and Craig, two of the nicest guys you'll ever meet, and incredibly modest about that achievement, which of course was part of a big team effort. In the Pierce 2 months ago, they pushed this cave to 245 meters in a 16-hour dive in 6-degree water, which was a major challenge. I'll show you a couple of other photos from the Pierce a little bit later. Now, because of the popularity of this idea that bubble models and deeper stops were good, divers who liked the mathematical simplicity of Bullmann's model started using what we call gradient factors to force Bullmann's model to insert deeper stops and make it look more like a bubble model. And so since gradient factors are going to come up in the rest of this presentation, and it's a very popular approach to decompressing now, I should just quickly tell you what it means. So when using gradient factors, you choose two numbers. We'll get rid of that Bullmann decompression there. You choose two numbers, a lower number called GF low and a higher number called GF high. And basically the lower number is what controls the deeper stops, or the depth of your deepest stops. So if you choose 20, say, what that means is that you can ascend until you develop tissue saturation that is 20% of the allowable Bullmann limit, illustrated by that point I've just shown there. So this is 20% of the allowable limit at this depth. And so that will become our first stop. And then your GF high is the fraction or percentage of the Bullmann limit that you will allow at the surface. So you put that point in, 90% of the Bullmann limit, which is this yellow line here. And then you draw or interpolate a line between those 2 points, and that becomes your new supersaturation limit. And your decompression takes place not allowing any of the tissues to cross that limit. And you finally come to the surface with 90% of the Bullman limit. Now, obviously, the lower this number, the deeper the deep stops will be. And around that time, early 2000s, when gradient factors started to be used, it was very common for people to use gradient factors that strongly mimicked a bubble model. So GF low of 10 or 20, like I've got here. Okay, so that's just an introduction to what we mean by gradient factors, because this concept comes up further on. Now, I've sort of alluded to this already, but it is fascinating to reflect on the fact that this essentially worldwide adoption of bubble model or deep stop approaches to decompression using gradient factors was adopted essentially in the complete absence of any human data that supported the concept. It was all based on this idea that it must be better. It makes sense, and so it must be better. And the question now is, and this is where the rest of this presentation is going, is to say, well, okay, where do we sit today? What studies have emerged, and what are they telling us about these two differing approaches to decompression? Now, at this point, I just want to provide some objective evidence for the fact that I have a very open mind on this subject. And I do want you to understand that back in the early 2000s, I was just like everybody else. I thought that the argument for deep stop decompressions was compelling. The mathematics I couldn't really understand, but it made sense to me at a physiological level. And therefore, I, like everyone else, was an adopter. Because I have been accused, in these online debates of having an agenda against deep stops. That's absolute rubbish. I was using them. Sorry, Michael, I'm probably going too fast there, but so I'm starting to get passionate now and talk quickly. So I apologize. You're doing a fantastic job, by the way. So I was just like everybody else. And this screenshot here is an article that I wrote on an Australian diving website back at, this must have been around 2002, I think. And I just want to highlight a couple of lines here from down at the bottom. So it says, despite these cautionary words, and that was just pointing out that at this point, we don't have much evidence, actual experimental evidence. It seems likely to me that the use of these novel decompression algorithms based on bubble models will be properly validated in the fullness of time, and that their use will become more widespread. The potential benefits for all deep divers and technical divers are obvious. My words about bubble models and deep stops. And I just want you to be clear about that. I do not have an agenda either way. My only agenda is to the evidence. My only loyalty or my desire as a scientist is to follow the evidence. So without wanting to dwell too much on that, I just wanted to make that point. So what is the evidence currently available to us? Well, there are 3 published comparative studies in decompression diving by humans. There's 1 published non-comparative study of bubble grades after bubble model dives, and there are several relevant studies that are not published at this point. And I'll briefly mention those at the end, but because they're not published yet, I am loath to say too much about it. So the first of those comparative studies emerged in 2005 This came from a French group, Jean-Eric Blateau, a very prominent diving physician and physiologist, a very productive research group from the French Navy. Well, they were doing work on behalf of the French Navy and fundamentally trying to decide, I think, whether the French Navy would adopt a bubble model or stick with their gas content model that they were using at the time. And they performed a series of experiments comparing deeper stop approaches to shallower stop approaches using French Navy models. So these aren't Bullman or VPM or RGBM, the ones that we're familiar with, but they are nevertheless a gas content model and a bubble model. And I don't want to get too bogged down in detail, but 3 sets of experiments with this, in this experiment, a single dive, a gas content model decompression versus bubble model. In fact, this bubble model decompression was longer, so it's actually not a very good experiment for figuring out whether deep stops are a good idea. But what they found was, even though the bubble model decompression was longer, there were more bubbles later after the decompression in the deep stops dive than the shallow stops dive. And actually, to be fair, they showed more bubbles very early after the dive in the shallow stops approach. They had 1 case of decompression sickness in the deep stops group. In this repetitive dive experiment, where again the dives were different lengths with the different models, so it's a bit hard to interpret. The surface interval was constant though. They had many more bubbles at all times in the deep stops group, and then in this another single dive comparison there was no differences. But the upshot of this was that they declined to adopt a bubble model for their routine diving, as I understand it. Now, that study appeared in 2005 at the height of the sort of popularity or the growing popularity of bubble models in technical diving, and it was largely ignored. And look, you know, it's a small study, and actually a little bit difficult to interpret because, you know, some of their profiles, in fact, just about all of them were of different lengths. And as I spent time telling you earlier, it's difficult to interpret the effect of stop depth distribution on decompression when you have dives of different lengths. They've got to be the same length. Okay, then in 2007, one of my colleagues from Australia, another anaesthetist called Andrew Fock, he was probably the first, what you might say, whistleblower. Andrew's a very intelligent, perceptive guy, and he'd been reading the literature fairly extensively and wasn't convinced by the bubble model argument. Not completely. I mean, his article was balanced, but he was the first person to sort of say, hang on, we're adopting these models without any real evidence that they work. And in fact, there's some reason to believe that it might not be correct. But there's no original data in this paper. It's just an opinion paper. So we'll move on from that. Whoops. Then in 2010, this paper came out from Zeljko Duic's group in Croatia. And essentially this was some experiments where technical divers were doing 60 to 70 meter trimix dives and having bubble grades monitored after the dive. It was not a comparative study. So this is not solid evidence against or for bubble models either way, but it's important because they found consistently high bubble grades after surfacing from VPM controlled dives, despite the fact that the dives were all conducted perfectly according to the algorithm, according to the VPM planner. And when I say it's important, what I mean is it was one of the first studies that actually starkly put it in front of us that bubble models don't appear to control bubbles, because these divers had very high bubble grades after their dives. Now, like I say, not a comparative study. It didn't compare VPM with something different, but it did show that even if you adhere to the VPM algorithm perfectly, you still can have high bubble grades. In fact, they all virtually had high bubble grades. So that got people thinking even more. And now we'll move on to arguably the most controversial but consequential study of all of them, the so-called NEDU study, or Naval Experimental Diving Unit study. This is one of my photos from Truck Lagoon in November last year. That's Pete Mesley, who runs trips there. If you ever want to go to Truck Lagoon, you should think about going with Pete. His trips are just amazing. This is the Momakawa Maru engine room. You know, we all like gauges and engine rooms, so it's the classic gauge photo. So the NEDU study. This was published in 2011. The authors were Dave Dulett, who I've alluded to earlier, and Wayne Girth. Those two, between the two of them, you know, it's probably 90% of the world's decompression physiology expertise right there. Keith Galt, of course, also very knowledgeable, but Dulett and Girth, arguably the two best known decompression experts internationally. So they did this study where they ran immersed divers in the ocean simulation facility at NEDU. This is it here, amazing place. So they had they chose these two profiles. Now, there's a lot of criticism around this in relation to its applicability to technical diving, and I'll address that issue later, but let's just consider it on its own merits to start with. So this was a 170-foot dive, so just over 50 meters for 30 minutes, a working dive on air with decompression according to two different profiles. One, a US Navy gas content model, so, you know, similar to Bullman, but not Bullman, but same principle as Bullman, and a bubble model. Again, not one of the ones we use. This was a Navy bubble model, which produced deeper stops. These are the two profiles. So the yellow, the shallow stops profile, and the red deeper stops profile. Critically, the two profiles were exactly the same length. And that methodology allows you to comment on the effect of the distribution of stops and times. We'll be returning to this a little bit later when we look at its implications. So the divers were immersed, 30-degree water, doing exercise, which is 115 watts, about, you know, moderate thinning pace. And the water temperature was 30 degrees, and they had no thermal protection. So there was some degree of thermal stress, although 30-degree water is very warm. I'm sure most of you in Poland would consider that to be a bath. But the divers did get cold. So this dive had thermal stress and exercise stress. And the outcomes were decompression sickness. That was the primary outcome measure, and venous gas emboli. That was a secondary, measured by Doppler, a secondary outcome, actually by echocardiography. But the primary outcome measure was decompression sickness. Now that is, you need to reflect on that. They were doing experiments on humans where the outcome measure was decompression sickness. And very few studies get done like that in diving medicine. Virtually all decompression studies have gas emboli as the outcome measure, not decompression sickness. So from that point of view, this is a very unique study. And let's cut straight to the chase. They had 10 cases of decompression sickness in 198 dives on the deep stops profile, and 3 cases of decompression sickness in 192 dives on the shallow stops profile. And the study was stopped at that point because the difference became statistically significant. They were going to do more dives, but the ethics committee requirement was that if you get a statistically significant difference between the 2 groups, you have to stop, because essentially you've answered your question, and we don't want to take the risk of doing more harm to other subjects in the experiment by carrying on unnecessarily. So the study was stopped at that point. And on that basis, not surprisingly, the Navy declined to adopt bubble model decompressions for routine operations. So the question is, why did the deep stop profile fail in the NEDU study? And this study has been dissected and analysed and reanalyzed so many times since it was done, and the consensus agreement is that it was probably the effect of deep stops on later supersaturation in slower tissues that accounts for this outcome. Now, I'm going to illustrate what I mean by that, so bear with me. Remember, I showed you this diagram here, which shows fundamentally the difference between a gas content model like Bullman, where you're allowed to ascend to quite a large amount of supersaturation before you do your first stop. A bubble model, in contrast, will stop you a lot deeper to reduce the amount of supersaturation. The point of bringing this diagram back into play is to illustrate what is happening to a slower tissue than this one under these 2 different decompression scenarios. So let's consider a tissue that has absorbed less inert gas during the time at the bottom depth and is now sitting about here. Now, can I say again that this diagram is a simplification? It's not to scale, it's just attempting to illustrate a principle. So what happens to this tissue in a Bullman style decompression, where we ascend quite a long way to the first stop? Well, during that ascent, it'll be taking up a very, very small amount of inert gas, but not much, until it reaches that green line there. So that's what is happening with this slower tissue during this Bullman style ascent. Let's now look at what happens to it when you start imposing these deeper stops. So what that means is that during these stops, this tissue will still be accumulating inert gas. Now, look, this diagram has been criticized for exaggerating the extent to which this occurs. And I accept that criticism. It is, it's just illustrating a principle. The point is that when you're stopping deep to protect your fast tissues, your slower tissues will still be taking on inert gas. That's the point. And we'll look at some more accurate quantification of that now. So did this really happen in the NEDU study? Did the protection of fast tissues from supersaturation early in the ascent by stopping deeper, like I'm showing here, did it really result in these slower tissues taking on more inert gas and being more supersaturated later? Let's have a look. Now, this is where we first encounter these fantastic diagrams done by Kevin Wats. So he refers to them as heat maps, which is what they are. Now, don't get put off by this. They're easy to interpret, and in fact, they make understanding this issue so much easier. The first thing to understand is the scale at the bottom. It's time in minutes. Remember, the NEDU study was a 170-foot dive, just over 50 meters, for 30 minutes. So this is 30 minutes into the dive. You see that first number there is 32. So that is the point of leaving the bottom. And this is the point of surfacing. And the next thing to note is that there's lots of little lines on this diagram. And they're numbered from 1 to 16. Now, in fact, what they are, we'll just zoom into it. Each line represents one of the 16 Bullman tissues. And number 1 is the fastest tissue, and number 16 is the slowest tissue. So going back to the diagram, these are the fast tissues, these are the slow tissues, and this is what is happening to them over time. Now, the hotter colors indicate supersaturation. So red is high, orange is highish, yellow is, somewhere in between. And then these colors here indicate on-gassing. So remember I said that early in the ascent, a fast tissue will be off-gassing and potentially becoming supersaturated, whereas a slow tissue will still be taking on inert gas. So, high on-gassing is this kind of whitish color, then purple, then blue, less and less in-gassing. So here we are, just leaving the bottom and ascending to our first stop on the NEDU shallow stops profile, which brings you quite a long way towards the surface to your first stop. And what you see is high supersaturation in the fast tissues early, exactly what you'd expect when you ascend a long way to your first stop, but relatively low on-gassing in the slow tissues because you're getting shallow a lot quicker, so your slower tissues are taking on less inert gas. And then low supersaturation in your slow tissues later. Now remember, this is the profile that had less decompression sickness. Let's now look at the deep stops profile and see how that looks in terms of this distribution of supersaturation across the different tissues. So here's the deep stops profile, and you can see that it is virtually the opposite. So what you see, compare it. Early on in the ascent, you don't ascend very far, so you have less supersaturation in those fast tissues early. You can see it. Here's a lot of red in the fast tissues, early high supersaturation when you come up a long way, whereas in the deeper stops, you protect those fast tissues from supersaturation. But compare the on-gassing, more on-gassing in the slower tissues, and then later, a lot more supersaturation in the slow tissues when you get to the surface compared to the shallow stops profile. So a very different distribution of supersaturation across these tissues. And it's abundantly clear from those diagrams that the navy deep stops profile did reduce supersaturation of fast tissues early in the decompression. There it is. Look, there's the deep stops profile, way less supersaturation in those fast tissues. But that didn't seem to be protective, because the outcome was that the deep stops profile had more decompression sickness. And it must be, if you're saying, okay, well, why is that? The only disadvantageous difference in that deep stops profile was that there was more supersaturation in the slower tissues late in the decompression. That's the most plausible cause for the increase in decompression sickness in the deep stops profile. Okay. Well, as I alluded to before, those profiles have caused a lot of controversy and argument in the technical diving world. So people say, but the NEDU deep stops profile is different from profiles generated by VPM. It's not the same. And they'll say it didn't have any real deep stops. Well, okay, let's put in some real deep stops. So this is that diagram I showed you of the two profiles earlier, but now I've imposed another profile, the green line here. You can see it. So that is a VPM profile with enough conservatism to be the same length as the NEDU study profiles. And it actually turns out that for those of you who know about VPM, it's about VPM +7. So in the software that you can purchase, it goes up to +4. But within the mathematical model of VPM, it is completely legitimate and part of the model that you can have higher levels of conservatism beyond +7, actually. But this is VPM on very high conservatism, +7, and it makes the decompression very long, as you'd expect. But these are VPM generated deep stops right there. Now, if we go back to the heat map analysis and include VPM style deep stops, we can have a look at what difference that would make. So here are those two diagrams I showed you before, the NEDU shallow stops profile, the NEDU deep stops profile, and another heat map, again, all of this generated by Kevin Watts, for VPMB +7 on the same dive. And you can do the comparison for yourself, but this is the profile that had the least decompression sickness. The deep stops profile is the one that had more decompression sickness. And you tell me which one VPMB +7 looks the most like. And then ask yourself the question, why would you expect the result to be any different if you used VPMB +7 compared to either of these profiles? Remembering that supersaturation is the driving force for bubble formation. And I found this very confronting for someone who, until the NEDU study came out, was essentially a bubble model advocate, albeit with some concern that we didn't have high level evidence to support it. But this started to change my mind for sure. Now, there's another analysis that's worth looking at in relation to these dives. Remember I showed you before how you can calculate what we call integral supersaturation. So for all of the tissues, let's use Bullman's 16 tissues, you can generate a curve that looks like this. So on gassing and then off gassing after the dive. And you can look at this period in here where the tissue gas pressure is higher than the ambient pressure, so it's supersaturated. And you can calculate the integral of time and supersaturation to give you an index of the supersaturation stress that's driving bubble formation, or the integral supersaturation. And you can add that up for all the tissues, and it gives you a single number that is an approximate estimate of the decompression stress associated with that dive, bearing in mind that supersaturation drives bubble formation. So let's do that for these NEDU profiles. Again, Kevin Wats's diagram. So this is integral supersaturation in pressure time intervals, so in pressure time units, so millibar minutes. This is the deep stops profile, NEDU, VPMB +7. Here's the NEDU shallow stops profile. And here is a gradient factor profile, 53-53. Why 53-53? Because that gives you a decompression the same length as all of these other decompressions, which allows us to compare them in terms of the distribution of stops and times. And you can see the answer for yourself. The NEDU deep stops profile had the highest integral supersaturation. You get slightly less with VPMB +7 with enough conservatism to be the same length. But these shallower stop approaches have much less integral supersaturation. So again, a reinforcement of this idea that not only is the distribution of supersaturation different, but the total supersaturation is less in the profiles with less emphasis on deep stops. Okay, this is a photograph. This is one of my photos from the Pierce Resurgence. It's actually a self-portrait. Pete Mesley has been teaching me how to do his amazing light painting technique. And this is a photo showing the 40-meter habitat that we put in there. This vertical shaft goes straight down to 114 meters, and then it flattens out and keeps going at a less steep angle. And this is it's actually a composite image of 3 or 4 photos using light painting techniques, and that's me. You can see me there in the picture. And before you give me any shit about my trim, I've wedged myself into the rocks there to try and stay still, because these are time exposures. So I mean, I can't stay in trim absolutely still for a 20-second exposure. I'm sorry. So that's why I look like that. But yeah, it's an amazing cave, 6-degree water, freezing cold. Anyway, another criticism is, well, you know, VPMB +7 and air diving is not what technical divers use. And so there's no link between the NEDU study and what we really do. Well, actually there is a link. It's an inferential one, but there is a link. And let me illustrate that to you. Let's take a dive that no one will dispute is a real technical dive, okay? Closed circuit rebreather, 83 meters for 20 minutes, a set point of 1.2 with 1050 diluent. Yeah, everyone recognizes what those parameters mean, or rebreather divers do. This is bog standard technical dive. And let's compare VPMB +4, which is definitely a level of VPM conservatism that is used out there. And gradient factor is 40/74. Why 40/74? Because 40/74 gives a decompression exactly the same length as VPMB plus 4. Well, that's what I've just said. So let's do the heat maps for those two dives. So here's VPMB plus 4 on that dive, 83 meters, 20 minutes, closed circuit rebreather, set point 1.2, 1050 diluent, standard technical dive. What you see is low supersaturation in the fast tissues early, exactly what you expect with a bubble model decompression with deep stops. You see high on-gassing in the slow tissues early because you're spending time on deep stops. And then you see high supersaturation in the slow tissues late in the decompression. Ask yourself which one of those NEDU profiles that looks most like. And then here's the 40/74, the gradient factors decompression for exactly the same dive, exactly the same length. So more supersaturation in the fast tissues early, but less on-gassing in the slow tissues during those deeper stops because they're short and shallower, and less supersaturation in the slow tissues late. So there's the heat map comparison of a bubble model or deep stops profile, which is unequivocally used in our modern technical diving era, and a gradient factors profile designed to have less emphasis on deep stops. And you can see that the bubble model decompression has all the features that were present in the NEDU deep stops profile, which had more decompression sickness. And if we look at the total integral supersaturation for those profiles, so those are the ones I just showed you, are indicated by these blue arrows. So VPMB plus 4 compared to 40/74, way less integral supersaturation in the gradient factors decompression. And there's another couple of gradient factor decompressions, all with the same duration of decompression shown here, 1082. That's a fairly deep stop oriented gradient factor choice, or even shallower stop gradient factor choice. So less deep stops, more shallow stops with 66, 66. Again, the same length of decompression, but less integral supersaturation. So this makes complete sense that 40/74 with less total supersaturation and the same pattern of supersaturation across the tissues that had less decompression sickness in the NEDU study would be a better profile. And that's essentially what this is saying. Here's the link with the NEDU study. What we see here in this modern bubble model approach that is used by technical divers out there now is the same disadvantageous pattern of supersaturation in the slower tissues late in the ascent, and the yellow bar, a greater total integral supersaturation in the deeper stop approach. Ask yourself, with those two factors combined, why would you expect a different result to the NEDU study? I mean, what magic has to be happening for there to be a different result? I can't think of one. I mean, I'd like to. If there really was one, I'd like to think of it, but I can't think of one. So the overwhelming likelihood is if you tested VPMB plus 4 against GF 40/74, the result would be the same as the NEDU study. The deeper stops approach would have more decompression sickness. That is the most likely outcome. We're nearly finished, by the way, Michael. You're doing famously, so thank you. The only other study that's come out that is relevant is this study that appeared from Pasquale Longobardi's group in Italy in DHM in 2017. And you can actually download this paper at this link. It's on PubMed Central. Basically, this was a comparison of a gradient factor profile versus ratio deco. And in fact, the gradient factor profile was 30-85. It's actually still got quite a strong emphasis on deeper stops. It's just that ratio deco has even more emphasis on deeper stops. So this is almost like comparing two deepish stop profiles. But anyway, you get the point. One has deeper stops than the other. Now, this study contained a design flaw when you're trying to compare different approaches to decompression, in that the ratio deco was 20% longer than the gradient factor decompression. You can see that in the profiles here. So it was 50-meter trimix dive, 1845, changing to nitrox 50 at 21 meters and oxygen at 6 meters. Same for both profiles. But here's the GF profile in the black, surfacing quite some time earlier than the ratio deco profile. And the outcome measures were bubble grades and inflammatory markers. And what they showed was a trend to higher bubble grades in the ratio deco group and greater production or secretion of these harmful, potentially harmful inflammatory substances in the ratio deco group. So let's be clear, despite the ratio decompression being longer by quite some distance, 20%, it was associated with worse outcomes on this study's outcome measures than the shallower stop approach of the gradient factor decompression. And if you look at the integral supersaturation of those two approaches, so here's the ratio deco and here is gradient factor 30-85, which had a shorter decompression, remember, 20% shorter, then even though the gradient factor decompression was shorter, it had less integral supersaturation, less driving force for bubble formation. You can see that here, not much, very small difference. But what if we actually had compared ratio deco to approaches to decompression that were the same length, but had different distribution of stops? Well, even VPM works better. So VPM plus 6 on a very conservative iteration of VPM, that's the integral supersaturation, and gradient factors 50-54, which has the same length of decompression as the ratio deco approach, way lower integral supersaturation. So for the same duration of decompression, by de-emphasizing the deep stops, you could have way less supersaturation driving bubble formation. So again, this analysis essentially predicts the outcome that they got. So look, in finishing, what does all of this mean? Well, I do want to make one point, and that is that I have found myself in the position many times in recent years of having to defend the science against unreasoned attacks. And what that has done is it's made the issue seem way more polarized than it really is. In fact, there's nothing wrong inherently with bubble models in the sense that, you know, you can't use them or you're going to die if you do. Nobody's saying that. The differences in actual risk between bubble model decompressions and gas content model decompressions with less emphasis on deep stops are probably small. I think that's what I say here. Yeah, it doesn't mean you can't use them. Differences in risk may be small, but I think what we can say with some degree of certainty is that bubble models probably do overemphasize deep stops. You know, it's a good concept. It was a great theory, but they've probably overdone it and they put too much emphasis on deep stops. The problem is that I can't tell you in an evidence-based way how far you should back away from bubble model deep stops, because there's no evidence that informs that for me. I can't give you, that's still work that's yet to emerge. But I think that a sensible approach is to back, if you're looking for optimal decompression, the current evidence suggests that we should be backing away from bubble model imposed deep stops to some extent. And the place I've ended up in is something like GF50. Now, I'm not recommending that to anyone. I'm just telling you that that's where my head, based on the evidence I can see, has taken me. It's not as deep as bubble models. It's not raw Bullman. It's somewhere in between. And over time, and with the emergence of further evidence, we'll get to a place where we can make recommendations that are more evidence-based. I mentioned earlier in the presentation that there are other studies that have started to emerge. There's one that has recently been mentioned on the internet, a study performed by Dan Europe in conjunction with Mark Powell in the UK, comparing two gradient factor decompressions, one with more emphasis on deep stops than the other. And based on the results that I've seen, it's confluent with the propositions that I've put to you here on this presentation today. However, I don't want to talk about it any further because I think that would be insulting to Mark and Dan Europe. It's their study. Let them present it in whatever means they want to, and no doubt it'll be published in the fullness of time. There have been a few other studies that point in the same direction, but again, unpublished at this point, and I don't want to talk about them because they're not my studies. But essentially, the evidence is confluent. And I think that what I've presented to you today is an appraisal of where we currently sit in May 2020 on this issue. And I hope that you found that useful. Some of this material can be found in this publication, which I'm happy to send to anyone who's interested. It was a review article on decompression from deep technical dives that I wrote with David a few years ago. And with that, I want to wind the discussion up and open it for questions.
Let's do the questions. So the question number one is, we have seen different gradient factor settings of 2090 versus 4074 versus 3085 in your presentation. Which one is the best?
Yeah, well, I kind of alluded to that at the end there. It's a great question, and I don't know what the answer is. I think I would summarize it by saying that, you know, an intelligent interpretation of that body of evidence that I presented to you would be that we probably shouldn't be starting our stops as deep as a bubble model tells us to, and we should back away to some extent from that. And there's some evidence in there that gradient factors around 20 or 30 are still too deep, and that something back around gradient factor 50 is more likely to be closer to the truth in the universe. And I can't tell you what that truth is because we don't have the data to answer that question. But that is why I've fallen at about 50. And in terms of the gradient factor high, which controls essentially the length of your shallow stops, I typically choose something like 70 or 80, but if I'm in an isolated place where I'm the only diving physician, it's usually 70, because that gives you quite a long conservative shallow stop decompression on high oxygen levels. And I think that that's probably the safest thing. So in the Pierce, cold water diving, the deepest dive I did was 125 meters. I did gradient factors 50, 70 for that dive. And that's where I've ended up. It's not a recommendation. It's just my personal appraisal of where the evidence sits at the moment.
Okay, thank you very much. The next question.
Can you hear me now, or?
Oh, I think, Michael, we can hear you.
All right. Okay. All right. So I can carry on with the questions then. Okay. The second question is why there's no more scientific data on decompression models comparison in technical diving? Are scientists behind those models not interested to compare and prove their model safety?
That's another great question. Look, the reason is that the testing required to demonstrate differences between decompression approaches with a high degree of confidence and statistical validity is an extraordinary challenge and incredibly expensive. Which is why I think the NEDU study is highly underappreciated by the wider diving community. I mean, what they did was extraordinary. And, 400 dives, all very carefully controlled, all precisely timed with respect to depth, all the conditions kept standard. These are the things you need to do if you're trying to figure out whether it's the decompression algorithm that makes the difference. It's a very hard thing to do, especially with decompression sickness as the outcome. So the answer to the question is, it's not that people aren't interested, it's just that it's so logistically difficult and expensive that it defeats most people's ambitions. There's very little money for diving medicine research out there. And that's why the few studies that are starting to emerge now, like the Italian study back in 2017, and this latest one that Mark Powell and Dan Europe have done, they're doing those with groups of divers in the field, trying to standardize the dives as much as possible, but that's actually quite difficult. When you're dealing with divers who just go for a dive, it's hard to get that right. But that's at least you can do that cheaply without it costing a lot of money. So the main thing is the difficulty and the cost of achieving those kind of studies. That's the problem.
Okay, so the next question is ratio deco dangerous? Yeah, that's the question.
Yeah, that's a very provocative, emotive question. I think this exact question or topic came up on an online forum a year or so ago. I think dangerous is the wrong word to use because it implies that A, we have a definition of danger in this setting, and B, we know exactly what the risks associated with decompression on ratio deco are, and I don't think we have the answer to either of those questions. I think what you can say with some degree of confidence is that ratio deco, certainly as it was tested in the Italian study, which is the UTD form of ratio deco, is associated with a higher risk of decompression stress or probably decompression sickness than a approach to decompression that involves less deep stops. That's probably what you can say, and probably not much more, but that's important information in itself. But I think trying to label it dangerous is unnecessarily emotive. I mean, lots of people dive with ratio deco, and decompression sickness is still relatively uncommon in that group. So I think we need to avoid labels like that. I just think what we should be doing is looking at the evidence as objectively as we can. And in that particular case, what the evidence is telling us is that ratio deco, as it existed then, it's been adjusted since then, as I understand it, overemphasized deep stops. And, a smart diver would probably not want to do that. So the idea would be to back away from those deep stops to some extent. But labeling it dangerous, I think, is just a bit provocative.
So we have few more questions on gradient factors, but I will come back to a question, to maybe a bit more general question, which is, can the tissues be trained and get used to supersaturation?
Yeah, now that's a really interesting question, and it starts to it gets into areas that I didn't cover. There is some evidence that there are strategies we can invoke that might make tissues less likely to form bubbles when they become supersaturated. It's not really training them. It's creating physiological circumstances that are less conducive to bubble formation. And look, you could spend a whole lecture talking about that subject on its own. But for example, there was a very interesting line of work which has been followed reasonably extensively that suggested that pre-dive aerobic exercise results in less bubble formation after diving in humans, and in much lower mortality or deaths in very provocative decompressions in animals. And it's not 100% certain why exercise would have that effect, but one theory, and a highly plausible one, is that the exercise in some way is conditioning the lining of blood vessel walls to make them less likely to form bubbles when the surrounding tissue becomes supersaturated. So in a sense, that is achieving what you're suggesting. It's like it's a form of training, not through repeated exposures to supersaturation, but through manipulating conditions where it'll make bubble formation from supersaturation less likely. And there's a few other strategies that have been looked at in that regard, but repeated exposure to supersaturation of itself, I don't think changes the situation. I think that it's creating a an environment where bubble formation is less likely to occur. Actually, there is some evidence too that if you do one dive a day, day after day, your bubble formation gets less and less each day. But again, it's thought to be that what's happening there is that repeated diving day after day is consuming the little micronuclei that bubbles form from, and making bubble formation less likely on the next day of diving. And we call that acclimatization, and it's a well-recognized phenomenon in diving. So in a sense, that's a form of training, but it's not just being exposed to supersaturation day after day. It's manipulation of the conditions that allow bubble formation to occur, which is the real issue. Yeah, sorry, complicated answer.
Thank you. So we will take 2 more questions. We have more, but we don't want to exploit you and use the whole Sunday for you. So the question is, how was Kevin Watts from your Kevin Watts heat map from your slides created? The divers had some kind of device installed during a dive. How that was created?
No, the heat maps are created based on the same modeling that is used in all the gas tissue content calculations for any kind of decompression model, whether it's a bubble model or a gas content model or Bullman or gradient factors. You calculate it's calculations of the gas content or gas pressures in hypothetical tissues. And in Kevin's case, he was using the 16 standard Bullman tissues, and based on the time depths and ascent rates, he would calculate the pressures of all the individual gases in the tissue in a constantly moving way, and then add up the integral supersaturation for each tissue into a single number. So no, nobody has ever measured gas in tissues in real time. I mean, there's no technology that allows us to do that. It's all based on mathematical modeling. But, that is the same approach for all the models. So when you compare VPM to a GF gradient factor decompression using that heat map technology, you're treating both models in exactly the same way. It doesn't disadvantage either one of the models. It's a standard approach to calculating tissue gas content.
And the last question is more from the recreational diving sector. What is the safest decompression for recreational divers doing actually no-stop dives?
Yeah, that's a really good question, Michael. And it's one that often gets confused with the argument over deep stops in technical diving. There have been 3 studies now that have looked at the effect of inserting a single, you could call it a deep stop or a deep safety stop, into the ascent from a no decompression dive at about half the depth of the dive. And the results of those studies are conflicting. One study showed that, so all of them used bubbles, venous bubbles, as the outcome measure. And one study showed that it reduced venous bubbles. Another study that, without wanting to get too complicated, was slightly superior methodologically because it kept the decompressions the same length, or they're not really decompressions, they're surfacing times, the same length. Showed that there was, the deep stop actually made it worse. And then there was a third study, which is a lot more complicated and hard to interpret, which on balance could probably be interpreted as being supportive of the concept of a single deep safety stop. And so the jury's out on that. But I think the issue with no decompression diving is that you definitely don't want to come up too fast. And you know, the ridiculous argument that can be made in relation to shallow stops. Oh, well, if shallow stops are better, why don't we just come straight to the surface? Well, of course, that's crazy. But it sort of has some relevance to this discussion of no decompression diving. It's still important to come up slowly. And so the safest way of ascending from a no decompression dive is to ascend at a safe rate, which I think most training organizations have focused now on 9 meters a minute as a maximum rate. Doing a safety stop is a good idea. A 5 meter safety stop is a good idea. And it may also be a okay idea to insert a deeper stop as a safety stop. What it probably does is just slows people down, and that's, if it works, that'll be why it works. But I think the key thing is just to ascend at the correct rate according to your dive training organization recommendations, and do a safety stop. And things are very unlikely to go wrong if you do that.
Okay, Simon, so that was all the questions for now. We won't keep you any longer. I would like to thank you one more time for giving us this wonderful presentation. It was as great as we all was expecting. Thank you for helping in our Nurkowie Pomagajmy Sobie initiative. It's very nice of you, especially that you do it early morning your time. So thank you very much for your time. Thank you very much for a huge part of the knowledge. And I hope we will have a chance to do something like that again.
It's a pleasure, Chimek. Next time I do it, I won't pre-hydrate to quite the same extent as I did this time. No, a real pleasure, and I thank you. And I'd particularly like to thank Michael for translating. That's a huge effort to listen to someone for over an hour and try and stay on top of the translation. That really was something. So thank you. I think he's gone now, but I really appreciate it. And yeah, anytime, you know, give me a microphone. I'm happy to talk. So yeah, safe diving, everyone, and look, stay safe in this COVID thing. You don't want to get it if you can avoid it. It's a nasty disease. It's not as benign as everybody thought it was at the start. It can be, but it often isn't. So stay safe, and yeah, safe diving too. Thank you.
Thank you. So be in touch. Stay safe.
Okay.
No dobra, moi drodzy, więc doszliśmy do końca naszej prezentacji. Ja bym jeszcze raz chciał bardzo, bardzo podziękować naszym tłumaczom. Wbrew pozorom to cały sztab ludzi, bo aż trzech, więc tak naprawdę masa ciężkiej pracy. Jeszcze dzisiaj rano ostatnie testy, które wykazywały pewne problemy, także duży stres z naszej, z ich strony. Mam nadzieję, że Wam się ten wykład podobał. Po raz już ostatni przypomnę, że cała nasza akcja ma na celu zbieranie pieniążków na pomoc centrum i bazom nurkowym przy trwaniu tego trudnego okresu teraz, więc jeżeli jeszcze nie mieliście okazji chociażby symbolicznej złotówki wpłacić na dowolne centrum, to bardzo, bardzo zachęcam. Link do strony znajdziecie w opisie. Michał, drugi Michał, Robert, Aga, bardzo, bardzo dziękuję za pomoc w organizacji tego wykładu. Tak naprawdę bez tej naszej wspólnej pracy to by się na pewno nikomu nie udało. Więc Michał, coś chcesz jeszcze od siebie powiedzieć? Powinieneś pewnie.
Zapraszamy na następne prezentacje. Przypomnę, że wydarzenia są już na Facebooku, więc możecie zapisać sobie daty kolejnych prezentacji, które będziemy mieli w ramach projektu Nurkowie Pomagajmy Sobie.
Do zobaczenia.